Hello, I am very excited to get to begin a brand new unit in our AP Calculus AB course. This is Unit 4, which I'm calling Advanced Differentiation Techniques. So we're going to be looking in this unit at some different ways to take the derivative, a couple different of them actually. We'll encounter a couple more formulas, just two more, the last two formulas that we're going to learn for taking a derivative. And finally, we'll look at our first application of the derivative, which seems to fit nicely into this unit. Our next units will focus more on different types of applications of the derivative. Today, we're going to be looking at a technique called implicit differentiation. So thus far, we've calculated the derivative only of what we would call explicitly defined functions. F of x equals, y equals, things like that. So just for reference, I've included a couple examples of explicitly defined functions, and hopefully, upon looking at this is something you think you'd be able to take the derivative of pretty easily. But in this lesson, we're going to look at taking the derivative of implicitly defined equations. There's an implicitly defined equation. Here's another one. Notice it's not solved for any particular variable, right? Perhaps we could solve for the variable, but we don't have to because we can take the derivative just as easily explicitly or implicitly. All right, let's discuss some things about notation. I want to discuss a little bit about notation before we go further into this. We have not really gotten too formal about our notation yet. We're just kind of slowly building up to that level of formality. We will get even more formal later on. But I like to just dive in and do the calculus and slowly kind of give you the theory of the notation. But now is a good time for us to go a little further. So I want you to suppose that y, w, x, and t are all variables that depend upon each other. And that's an important statement for what I'm about to say. In order for them to depend upon each other, it means the rate of change of one is related to the rate of change of the other. So let's start with the derivative with respect to x. That's how we read that. The d dx, we would say derivative with respect to x of y. Well, we've already seen this. If not explicitly writing it like this, we've already seen that the derivative of y is denoted dy dx. dy dx, dy over dx, change in y over change in x. And you can see what that's a nice handy notation, because if you think of this y as being y over 1, this works exactly like fraction multiplication. Now these aren't really fractions because d over dx is not a real number, it's an infinitesimally small number, but it does work out and it makes sense, right? So what would the notation for d dx of w? Well, I hope you agree it would be no different. We can say y equals and find the derivative. Surely we could say w equals and find its derivative, but its notation would simply be dw dx. Now we've talked about how we can also call these things like y prime and w prime, and that's short for y prime is short for dy dx. Well, in actuality, y prime is short for dy d whatever you're doing. So it has to be kind of implied what you're taking the derivative of, but typically we've been doing it with x, so that makes sense. But for most of this unit, I'm going to stick with the Leibniz notation and use d blank over d blank. All right, well, what would be the d dx of x? Well, we know the derivative of x is supposed to be just 1, right? Well, I want to point out that we can actually express it just like we've done here. We took the d times y, so we said dy over dx, dw, so dw over dx. I said times. It's not really a times, but the notation makes it work out that way, so it's familiar to us algebraically. So dx, that would be dx, and then I have dx. Well, this is a number going to x, and this is the exact same, going to 0, and this is the exact same number going to 0. So while 0 over 0, which is what this is, remember derivatives are limits, while 0 over 0 is an indeterminate limit, this is exactly the same number divided by exactly the same number. Now we know what that is. That's 1. So now we see another reason why the derivative of x is simply 1. Well, what would be the derivative with respect to x of t? Well, again, that would simply be dt dx, right? All right, well, what would be the derivative then of y with respect to y? Can we take the derivative of something with respect to a different variable? Well, of course we can. Wouldn't make a lot of sense if we had to only use x. Well, the dy would be, of course, dy over dy, which is just 1. Well, what about the derivative of y with respect to w? Can I take the derivative with respect to w? Well, I better be able to. If they're related, it's dy over dw. What about the dw dt? That would be that. The derivative with respect to x squared. Okay, so this time we're going to actually have to do some chain rule, right? So we're taking the derivative and we've got a composite function here. We've got an x inside an x squared. So that's going to be 2x, right? Because we bring down the power and subtract 1, 2 becomes a 1. So this was x times 2 to the first, but now I need to multiply by the chain, and that's the derivative of x, so that's dx over dx. So that's simply 2x times 1. Now, you would never normally show this extra step, and I'm not asking you to do so. That would be both confusing and kind of silly, but I want you to understand that we could say that it's there, right? So wait a minute. Now we got to take the derivative with respect to t of x squared. Well, this time I think this extra step might matter. Let's take a look. So we know that we have a composite function. We have an x inside a squared. So I pull down the 2 and I don't change the inside, just as x the first. But now I need to multiply by the chain, right? I need to multiply by the derivative of the inside. Well, that derivative, we did that earlier. You know, we said d dt of x is dx dt. So this time we actually do get something else here, right? We get this extra dx dt. And does that matter? Well, yeah, you bet you it matters. That's important. The derivative with respect to x of sine of y. Okay, so I've got a y inside a sine, so I have to use my chain rule here, right? Because it's composite. So the sine of y, the derivative of sine u, right? Well, you know that the derivative of sine of u is cosine of u. That means I don't change it, right? So cosine of u times u prime. Well, I need to take the derivative of y with respect to x, so that's dy over dx. And that is essentially is how we do implicit differentiation. We've basically been doing this whole time. It just hasn't really made a difference, but now it will. So let's take a look at finding dy dx for these implicit functions. For some of these, I've included the graph just because I think they're neat. When you're dealing with implicitly defined equations, you oftentimes don't have a function, y as a function of x, but you do get some really interesting geometry. And some of these curves I just made up myself because I've tried them. Others are kind of famous. So we'll take a look at these. Let's find the dy dx. So I'm going to take the derivative of y cubed. So I bring down the 3. The y stays the same, becomes a 2. And now I multiply by the chain. By the way, you can think about it as we're taking the derivative with respect to x of both sides. So it becomes more of an algebraic step. You know, we know that as long as we do the same thing on both sides, it's equal, right? So you can think we're taking the d dx of both sides. All right, I'll bring down the 2, and it becomes a 6y to the first times derivative of the inside, which we know is dy dx. Then minus 2x times dx over dx. Well, what is dx over dx? It's just 1. So do we need to write it? I don't think so. We don't need to write it this time. Negative 4 times, taking the derivative with respect to x of negative 4, well, that's the derivative of a constant. That's 0. Okay, so now the name of the game is we simply need to use algebra to isolate this dy over dx. And it turns out the algebra is pretty easy because we're going to be factoring out a common factor that's the power of 1. So the trick is to get every term that has a dy dx on one side and every term that does not have a dy dx on the other side. And usually you can do that in 1 or 2 steps. Sometimes you have to distribute first or something like that. This one here is pretty straightforward though. So I'm going to simply leave those 2 on that side and I'll add 2x to both sides, giving me that. I'll now factor out a dy dx from this grouping here. When I factor that out, I end up with 3y squared minus 6y is equal to 2x. Now I'll divide both sides by this. So when I divide both sides, I get dy dx alone, and I'm left with 2x over 3y squared minus 6y. So we see that the rate of change of y with respect to x is dependent not just on the x coordinate, but on the x and the y, which really, looking at the picture, shouldn't surprise us, because it looks like down here, this has a dy dx that would be horizontal, so 0, but over here, it looks to be quite different, right? And in fact, we have two of them, right? We have two different values we could possibly have there. So we notice that here's another example. Here's like a vertical tangent line, but on that same x coordinate is different. So we see that the y values make a difference, right? So there we go. All right, let's take a look at this next one. X squared plus xy minus y squared equals 3. We'll take the derivative with respect to x of both sides. So I end up with 2x. Ooh, what do we need to do here, though? That's a product, isn't it? We need to use the product rule. Many of these equations will have an xy term because it's just very common. So we'll say plus derivative of the first, derivative of x is 1 times y plus the first times derivative of the second. The derivative of y is dy dx. I should say now the derivative with respect to x of y is dy dx. All right, here I simply bring down the 2, y to the first times dy dx. And the derivative of 3, the other side, is 0. Okay, hopefully you remember that the name of the game here is to get all the terms that have a dy dx on one side and all the terms that do not on the other. Looks like this one again is not going to be too hard. Just subtract 2x and y. Then we factor out a dy dx. And I'll divide by x minus 2y. And so you can see the terms that had a dy dx end up being in the denominator, and the terms that did not end up being the opposite of them in the numerator. And that's the pattern that you should expect every time. Okay, let's take a look at another one. This is one I just kind of made up. I thought it was kind of neat to have the periodic nature, but writing on a exponential. Okay, so we're going to... Let's see here. Let's take the derivative with respect to x. So the 2 is just going to come along for the ride. And the derivative of x is 1. The derivative of e to the y. Well, the derivative of e to the u is e to the u times u prime. So it's e to the y dy dx. The derivative of 1 is 0. The derivative of cosine u is negative sine u, so the negative will cancel. So it's sine u prime. Okay, so I'll go ahead and distribute the 2. So maybe it would have been actually easier to do that from the beginning, but it gave us a good chance to remember out of hand that constants, when there's no exponent, don't affect anything. Okay. And I will leave the 2 there, and I'll bring this 2e to the y dy dx over here. And I have plus sine y dy dx. And so now we can factor out a dy dx. And divide. So we end up with 2 over 2e to the y plus sine of y is equal to dy over dx. So this seems to be implying that this function's derivative value actually only depends on the y value, which is interesting. You could see that while this is definitely not a function, this graph is not a function of x, but x is a function of y. This graph actually passes a horizontal line test, and therefore it shouldn't be completely surprising that we could get a derivative that doesn't have an x in it, because the slope of this tangent line does seem to only depend on that. All right, I got a few practice problems for you to do, so please pause the video, work through them. You can get the notes from my webpage, my Jed Wilshire. Just Google that if you don't have it. And so here you go. Just pause the video and work them, or you can do them one at a time and have me work them, but make sure you pause it and take time to practice each one. Okay, let's see how you did. All right, I'm going to take the derivative with respect to x, so this becomes a 2y dy dx. Then on the other side, I get to use the quotient rule. So low d high. Well, I'll do it in order of the little saying. So there's low, there's d high. 3x squared minus high d low, all over low low. So all I need to do is divide by 2y. And I'll just make this a plus x cubed. And when you divide a fraction by 2y, you can think of it as multiplying by 1 over 2y like this on each side. So the 2y just goes down here to the bottom. Okay, there we have it. Okay, this is somewhat of a famous curve, this kind of cycloid kind of thing. Kind of neat. All right, let's see how you did with this one. All right, I'll take the derivative with respect to x, so this becomes 2/3 x to the negative 1/3 plus 2/3 y to the negative 1/3 dy dx is equal to 0. Okay, so I need to get this over the other side. Okay. And then from here, you can see that I've got this 2/3 on each side. So let's just divide that out. I'm going to divide both sides by 2/3. So this just becomes a negative 1. And so then I have dy over dx is equal to x to the negative 1/3 over y to the negative 1/3. And I usually don't emphasize simplifying, but I do think it's kind of interesting that this ends up being the cube root of y over the cube root of x, if you didn't, when you move that around. So it's just kind of an interesting thing. You could even say that that's equal to y over x cube rooted, so or to the 1/3 power. Pretty interesting derivative, I'd say. Okay, here's another one. This is another one I made up. I love mixing exponentials with sine. I love the fact that they give this kind of repeated pattern that, really gives me something interesting. These regions that repeat because of the period nature, but also change because of the e to the x. Let's take the derivative. All right, we're going to need to use our product rule here. So the derivative of the first is e to the x times the second, plus the first, which is e to the x again, times derivative of the second, which is cosine of x plus cosine of u is cosine u times u prime. So now I got to multiply that by u prime. Make sure you put it in parentheses. Derivative of x is 1, derivative of y is dy dx. And derivative of 1 is 0. So this is one of those situations where, to avoid getting kind of stacked fractions, I am going to go ahead and distribute. So let me give myself some room here. So I have plus e to the x cosine of x plus y. I need to multiply this whole thing, right? This whole thing times 1, and then that whole thing times dy dx. So I'll get just that plus 1 plus the same thing. Oh, I thought I changed color back to black. Plus the same thing, e to the x cosine of x plus y times dy dx is equal to 0. So when I move everything over, we'll end up with negative e to the x sine of x plus y plus e to the x, oops, that's not a plus. That's a minus e to the x cosine of x plus y. And that was times dy dx. So lastly, we should have that dy dx is equal to negative e to the x sine of x plus y minus e to the x cosine of x plus y all over e to the x cosine of x plus y. So we could probably do some pretty interesting things there. We could rewrite this as a fraction minus 1 or something like that. All right. For our next problem, we have some examples to do again. We're going to look at doing a little bit of analysis on these derivatives. So I've got a picture of the curve here. This is a neat little curve, I think. But I took off the units so that, I don't want to spoil the surprise for some interesting aspects of the curve, like where the derivative is. We're used to finding when the derivative is horizontal. We know that corresponds to some important points, but also now we can look at when the derivative is vertical. So notice how we handle that. So let's find dy dx here. We have 2x plus 2y dy dx equals 3x squared plus 2, and the derivative of y is, again, dy dx. Get all my terms that have a dy dx on one side. I'll just move them over here. And I'll move all my terms that do not have a dy dx to the other. Then I can factor out a dy dx. And I think some of you are probably already starting to kind of skip that factoring out step since you know what the result's going to be. It's going to be just dy dx, and everything that had a dy dx ends up going into the denominator. And there we have it. All right, we're going to find all the points where the curve has a horizontal tangent line. Well, a horizontal tangent line is when dy dx is equal to 0. So in order for this to equal 0, we need the numerator equal 0. So I'll say 3x squared minus 2x is equal to 0. And I can actually solve this. Sometimes you have to solve and do a substitution in the original equation. I can actually solve this one, though. So I get x equals 0, and 3x minus 2 equals 0. So 3x equals 2, and so x is equal to 2/3. Now, don't get carried away here. There's no guarantee that either one of these x values actually correspond to a horizontal tangent line, because it could be that the curve is not defined at x equals 0. That happens a lot. I don't think that's going to be the case here, but you can see that, say, if we got a horizontal tangent line at like -10, maybe -10 is not on that. It may not be there. So you have to go back and check, which we need to do so regardless, because we need to find the y coordinates. So let's go in and check. So I'm going to plug a 0 in for x in the original equation. So when I do that, I get 0 plus y squared is equal to 0 plus 2y. Okay, so that's a polynomial. I need to set it equal to 0, and so I get y equals 0. Well, I'm jumping ahead of myself. Y, when I factor it out, I actually get y equals 0, and y is equal to 2. So that tells us that we have a couple of points. We've got 0, 0, and this up here, where it's horizontal, must be 0, 2. All right, now we got to handle the 2/3. So I've got 2/3 squared plus y squared is equal to 2/3 cubed plus 2y. So this becomes a 4/9 plus y squared equals 8/27 plus 2y. And this one's not going to be as fun to solve. I'm going to multiply both sides by 27. So 27, like so. 27 divided by 9 is 3. 3 times 4 is 12. And then that becomes 8 plus 54y. All right. And so that becomes 27y squared minus 54y equals 4, or plus 4 equals 0. I don't know if that's factorable or not. Let me think for a second. Here, 27 times 2 is 54, but yeah, probably not. So we probably have to use the quadratic formula. So opposite b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And so, believe it or not, I'm actually just going to leave my answer like that. So 2/3 and then 54 plus or minus the square root of 54 squared minus 4 times 27 times 9 all over 54. Okay, so let's go on to the next. Okay, now we're going to find the y-coordinate of all the points of the curve as a vertical tangent line. So a vertical tangent line is when you have some number like 1 over 0. So we need to solve for when we have 2y minus 2 equaling 0. Because a vertical tangent line means that we have a real number in the numerator that's not 0 divided by 0 in the denominator. That's an undefined slope, a vertical tangent line. So 2y minus 2 equals 0. That is y equals 1. You can look at the graph and confirm that that definitely appears to be the case. To find this value would be very difficult just because of this equation. So that's why we're just going to find the y-coordinate. But I do want to talk about how can we confirm, if we didn't have a graph, how can we confirm that this actually does indeed occur on this curve? You can see it appears from the curve that the graph that every y value actually is reached, but not every x value. So it's a good idea for us to be able to practice that. So let's practice confirming that this value of y does indeed occur on the graph, even though we're not going to solve it. So I'm going to plug in a value of 1 for y, and I get x squared plus 1 equals x cubed plus 2. And then what I want to do is I want to look at what that's saying. So I have negative 1 equals x cubed minus x squared. If I put So what I really have here is this is some function f of x, and I'm asking does it ever equal negative 1? Well, let's evaluate f of negative 3. Well, f of negative 3, if we let f be x cubed minus x squared, well, that's a negative 27 minus 9. That's a negative 36, right? And let's do f of 2. Well, f of 2 is 8 minus 4 is 4. So you can see that we have two x values, one at negative 3 and one at 2, that result in output that surrounds negative 1. And since f is continuous, we could say by the intermediate value theorem, we know for sure that there must be some x value where this takes on negative 1. So that means that there must be some x value that corresponds to y equals 1. So we definitely know that there is a vertical tangent line, which would be an interesting question. Can you confirm whether or not this graph has a vertical tangent line? We solve for the y value 1, and we use the intermediate value theorem to confirm that it must occur somewhere. All right, I want you to do this practice problem, so pause the video, or you can do it one step at a time, but make sure you work it before me. So give it a try. All right, we're going to find dy dx in terms of x and y first. So we'll use the product rule. Derivative of the first times the second plus the first times derivative of the second. All right, and then that's 3 dy dx minus 10x equals 0. So we'll get all the terms that have a dy dx on one side. And we'll factor out a dy dx and divide by what was left over, which was x plus 3. All right, we've been asked to evaluate dy dx at the point 2, 4. Note, we do need to use both the 2 and the 4 since our dy dx is dependent on both x and y. So we have 10 times 2 minus 4 over 2 plus 3. Now, if this was a free response question, which it often is, I would just stop right there. But just for fun, let's go ahead and evaluate. That's 20 minus 4 is 16 over 5. So 16 over 5 is the slope of the tangent line at the point 2, 4, which, would be somewhere over here. Let's write the equation of the tangent line to the curve at 2, 4. Oh, it's maybe been a while since you've done that. So y minus the y-coordinate equals the slope times x minus the x-coordinate. Piece of cake, right? At which points, if any, does the curve have a horizontal tangent line? Well, let's go back and look at the derivative. I'm just going to copy and paste that for us. So our derivative is 10x minus y over x plus 3. A horizontal tangent line is when you have a 0 in the numerator. So I'm going to solve that. 10x minus y equals 0. So I have 10x is equal to y. Well, what does that mean? Well, that means I need to plug it back into my original equation. So let's go get that. And we have to use a substitution. I kind of hinted at that earlier. Of course, you know me. I like to be evil on the practice problems, make you do something you haven't done before. All right, so let's do this. Maybe this won't be too bad. So this becomes x. Oh, I'm still on select tool. All right, x times 10x plus 3 times 10x minus 5x squared equals 0. So that becomes 10x squared plus 30x minus 5x squared equals 0. So that's 5x squared plus 30x equals 0. So at x equals 0, when I factor that out, oh, I'm getting ahead of myself. Let's factor out, actually start factor out of 5x. Now you can see that the solutions of that polynomial are 0 and negative 6. So at 0 and negative 6 on the x value, apparently we have a horizontal tangent line. Well, let's see here. What would our y value be there? Y value would be negative 60. I'm not seeing that on the curve shape I gave, but there must be some other branch down here below. That's got to be the case. I'm curious now. I'm going to pull that up on Desmos because I had a little picture of it. I would not have expected that. xy plus 3y minus 5 squared equals 0. All right, so let's see. We got the graph there. Are you going to come up? Are you going to show me something down? There it is. There it is. I'll be darned. Look at that. Going to have to update that picture, aren't I? Okay, that's all right. We can do that. All right, let's see the next one. At what point, if any, does the curve have a vertical tangent line? A vertical tangent line occurs at x when x plus 3 equals 0. So let's do that. So x plus 3 would have to equal 0. So that's at x equals negative 3. All right, well, that's not too bad. Let's plug it into the original equation. So I have negative 3y plus 3y minus 5 times the negative 3 squared has to equal 0. Ooh, what happens there? I end up getting negative 45 equals 0. That's no solution, right? So it turns out this x coordinate must not actually occur. And it does definitely look like there is when you look at the graph, there's definitely a gap at negative 3. So that x coordinate does not occur. So we're going to have to say there's no vertical tangent line. All right, got a little foliate, I believe is what we call that. So let's do one more practice problem. Pause the video and give it a shot, please. All right, so dy dx hopefully is becoming somewhat easier for you now. So 2x, right, plus 3y squared dy dx. And then we have to use our good old-fashioned product rule. Derivative of the first is 1 times the second is y, plus the first x times derivative of the second. Then we'll just get everything that has a dy dx on one side, and everything that does not on the other. And I'll factor out dy dx, which will give me 3y squared minus x on the left, which I'll then divide by. So it's going to end up looking like this. All right, what points, if any, occur where there's a horizontal tangent line? Well, that's going to occur when y minus 2x equals 0, which means y has to equal 2 times the x. Let's plug that back into the original equation. So x squared plus 2x cubed equals x times 2x. So that becomes x squared plus 8x cubed equals 2x squared. Now we can get that equal to 0 since it's a polynomial. So minus x squared equals 0. I'll factor out an x squared, and I have 8x minus 1. So it appears that we have it at x equals 0 and at x equals 1 over 8. But notice that it doesn't really look like a horizontal tangent line there. So what's happening with the x equals 0? We've got more of a vertical tangent line. I agree with the 1/8, but what's happening there? Well, if x equals 0 and y is equal to 2x, we'd actually get 0 over 0. So let's take a look at that. So I'm going to plug in 2x for y, which would be 0. So I'd have 0 minus 0 over 0 minus 0. Well, that's indeterminate. So I'm actually going to throw this one out as a solution because that's not going to actually do anything. And we can see that from the graph. So instead, it looks like the only horizontal tangent line is going to occur at x equals 1 over 8. All right, let's try the next one. Find all the points, if any. Oh, we forgot to finish finding the points. So the y here would be 1/4. So we think the coordinates is 1/8 comma 1/4. Well, what about a vertical tangent line? Well, a vertical tangent line occurs when the denominator is equal to 0. So that's 3y squared minus x equals 0. And if I solve that for x, I get 3y squared equals x. All right, so now let's plug that back into the original equation. So let me just copy that right quick. Okay, so I'm going to replace x with 3y squared. So I have 3y squared plus y cubed equals 3y squared times y. So this becomes 9y to the 4th plus y cubed equals 3y cubed. I'll subtract over the y cubed, so I end up with a negative 2y cubed equals 0. And I'll factor out a y cubed, and I get 9y minus 2 equals 0. So I have y equals 0, and I have y is equal to 2/9. So once again, we're getting that y equals 0 point again. Let's take a look at what would happen at y equals 0. Well, there does appear to be a vertical tangent line, but there's another tangent line that's not vertical. So we're really getting, can we say what the derivative is at that point? Well, we really can't. And again, if you plug in y equals 0, and if x is 0 to this original derivative, you're actually getting 0 over 0 again. So I'm going to have to remove this because that's not giving me a real limit. All right, so we have y equals 2/9. So 3 times 2/9 squared is equal to x. So that's 3 times 4 over 81 is equal to x. So 12/81. So we're going to say 12/81 comma 2/9. That is the point of a vertical tangent line, which must be, kind of right here. So we could get that one and we could get that one. And it looked like something interesting happened at 0. That point where it crosses is always this value here is always going to be a problem for us for a derivative because we've got more than one of them. So just be looking out for those. Okay. That's the end of this lesson. Some tricky stuff there, some interesting things to think about. Notice that the pictures help. When you get the picture, use it, and remember about, those points of crossing are not really going to work out, even though you oftentimes get them as a special value. And I will see you in the next lesson.